Excellent. So there's two things that I want to do today. First, I want to talk a little bit about how we might evaluate either new or existing emergent constraints. And then if we find several constraints that we actually trust, how we might combine them together to provide a better constraint on climate sensitivity. And so a lot of people have in the past said, don't read my paper, you're always so negative, you'll find something wrong with it. And so I wanted to just start out by saying that I really think that there are real emergent constraints. And in particular, at the bottom of my slide, this snow albedo, I think, is something that we all believe is true. And it certainly has stood the test of time in CMIP 3, 5, and 6 models. There's different flavors of emergent constraint, but the one that I think about most are kind of timescale invariance, and particularly related to cloud processes, where we know that it's the same processes that are controlling response to internal variability and response to warming. And so, so really, emergent constraints in some sense must exist. And so kind of along those lines, in terms of these processes that should be operating at every time scale, I want to talk about lower tropospheric stability, which is not in itself an emergent constraint, just because climate models do such a bad job at capturing response of stratocumulus to inversion strength and other conditions, but it should be an emergent constraint. And I think it's really an interesting case study. And so in particular, lower tropospheric stability is the potential temperature at 700 millibars minus the potential temperature at the surface. It was popularized in 1997, so it's quite hallowed. And looking at the top right plot, you see that it does, that lower tropospheric stability on the x-axis does a great job of predicting cloud fraction on the y-axis for tropical points, basically. If we could get a similar correlation from our emergent constraints, we'd be very, very happy. And there's a good physical reason for this to occur, that lower tropospheric stability is actually a good proxy for the inversion strength. And we know that for stratocumulus, the stronger the inversion, the less entrainment of warm, dry air from the free troposphere happens, the shallower your boundary layer, and therefore the more moisture that can stack up against that and form clouds. So it makes sense. And it works really, really well in the subtropics. It turns out that the reason why it doesn't work so well in the mid-latitudes, which I've circled in the top plot, is because 700 millibars is not the top of the boundary layer. And so you need a correction factor between those two. And in the tropics, horizontal temperature is essentially homogeneous everywhere. So you can use the same correction factor and everything works fine. But in the mid-latitudes, that's not the case. And so this all comes back to global warming and timescale invariance, in that we know that the tropical free troposphere is going to become more stable as the planet warms. And this is just the lapse rate feedback. And so lower tropospheric stability is going to increase in the future, even if your inversion strength stays the same. And so as a result, if you use LTS, you predict in kind of your emergent constraint way that you have a strong negative feedback in stratocumulus clouds, less climate sensitivity. And that's not actually the case, that you should do something more specific. You should use something like the estimated inversion strength of Wood and Bretherton, which basically just corrects LTS for the free tropospheric lapse rate. And when you do that, you get a much more neutral prediction of warming. And so I wanted to bring this up because I think that it serves as a case study in why we need to precisely understand the physics of the constraints that we propose, because I think otherwise we're likely to get something that seems real and actually isn't. And so this brings me up to a question, and I have a number of questions in this talk, maybe more than conclusions. But lately, I've been feeling like this need for physical explanation really makes the kind of pillar of emergent constraint research. Eventually, I think it's going to be indistinguishable from the long-standing pillar of process understanding research within climate science. I think the two are going to merge more than they have. So next I want to talk about out-of-sample tests and statistics. And so Manuel Schlund did a nice job of talking about this a little bit this morning. And so basically the punchline, both from my 2018 paper and then in spades from Manuel's paper, is that most of these emergent constraints, when we face them with an out-of-sample test with new data, they seem to fail. And so this is very frightening. Another facet of the same issue is both in my paper on the two left-hand side plots and then Manuel's paper on the right-hand side, we found that for certain constraints, if we made small changes to the number of models or the composition of models we used for our analysis, we got very different answers. And this could be that we added models and all of a sudden correlation became horrible, but it could also be that we add models and correlation got a lot better. And so for my 2018 paper, where I was trying to decide whether I trust existing emergent constraints or not, this totally confused me because sometimes I would think, oh, I can't trust that model. And then I would add a few more I can't trust that constraint. And then I would add a few more models and all of a sudden things would work out. And so I think that this really, both of these points just lead to the conclusion that the number of independent samples that we have in each CMIP archive is too low to robustly identify new constraints or to disprove proven constraint or previously proposed constraints. And so I think that maybe one of the top things this community needs to do is to improve our sample size. And Steve Sherwood pointed out to me a couple of years ago, the obvious thing to do here is to pool the CMIP ensembles. So once you get up to like 100 samples, even if they're not uncorrelated with each other, it's going to be a lot harder to get these large correlations by chance. So of course, then you don't have any out-of-sample data to compare against immediately, but I think that we're probably going to see a lot less false positives if we did that. And then I just want to point out the Voladin constraint. You'll notice is proposed in CMIP3. It also was highly significant in CMIP5 and in CMIP6. And so this is something that I haven't heard a lot of people talk about as being something that is potentially real, but I think it's something that deserves more attention. So now I want to shift gears a little bit and talk about how we would evaluate existing emergent constraints. And this is basically, in this context, just to kind of pave the way for saying why I think we should think about combining emergent constraints. And so in this 2018 paper, what I did is to just note that if you have a correlation between an emergent constraint and ECS, you could write that as a sum of the correlations between your emergent constraint and each of the forcings and feedbacks that contribute to ECS. And then you can use that to decide whether a particular constraint that has a physical mechanism related to, say, subtropical stratocumulus is actually due to subtropical stratocumulus. So it gives you trust that the model is or that the constraint is working like you think it is. And so you can do this both breaking down by feedbacks and forcing, and you can also do it by geographical regions. And so that's what I did on the plot on the left. And the result of that was that I was able to say which constraints seemed to be passing all the tests and which didn't. And in particular, I've found that for constraints, so Sherwood D, the Briand-Chalinis constraint, the Xi constraints, and the Briand-Talbido constraint all seem to pass all of the tests. So I see this as growing evidence that some of the constraints are real, and that brings up the question that we might want to combine these emergent constraints to get an even stronger constraint. And so then I also want to ask the question of this community. So based on my 2018 paper, particularly since it does matter the details of which models you include and which you don't, what kind of answers you get, I don't think that it's a complete validation of these constraints. So what else needs to happen before we completely trust them is, I think, an important question. And so for the rest of this talk, I'm going to just ask the question of how we would combine emergent constraints together if we have several that we trust. And so just starting out on a philosophical sense, I see there being two ways that you can combine constraints. So one, you can constrain individual processes contributing to ECS and then combine the results to get a constraint for ECS by itself. And this, in my impression, is what Steve Klein did in his chapter of the WCRP ECS assessment. And so in this case, it was process level understanding rather than emergent constraints he used to get predicted values for each different type of cloud feedback, but we could do the same thing with emergent constraints as well. So because the total cloud feedback or feedback in general is the sum of individual feedbacks, once you've constrained each individual one, you can sum them up and get the total feedback. And so I think that this would probably be the best thing to do because it really focuses on process level understanding. So I think we'll have more trust in it. But I also think that we're not in a place where we can do that yet because we don't have emergent constraints on all of the different feedbacks that we need to. So in light of that, I'm going to spend the rest of the talk doing the opposite, which is saying, so suppose each of these emergent constraints that I have on ECS is basically a flawed sample of an ECS predictor. And so how would we combine them? And so in this Bretherton and Caldwell 2020 paper, we came up with what I think is a really simple and easy to understand method that solves the problem. And so the approach is as follows. So if I have an emergent constraint X and something I want to predict in the future climate, so ECS, which is Y in this case, and I assume that these two follow a bivariate Gaussian distribution. So that's a big assumption, but I think one that's probably hard to get away from. Then just the definition of its bivariate Gaussian PDF is what I wrote in the top equation, which depends on a vector U, which is just the values of ECS and your emergent constraint. And in particularly, it depends on the covariance matrix of that vector. And so, so that's all pretty, well, I guess what I should say before I move on is that then you can obviously just get the probability of having a certain ECS as being the value of the conditional PDF where you have evaluated at your particular value of X. And so that's shown in this graphic on the right where I have the PDF of the observed data along the y-axis. You take a slice through it at the maximum likelihood value, and you look at how that projects onto, in this case, the green and the teal lines are isosurfaces of that bivariate PDF. And that allows you to just project the result down to get a PDF for ECS. And you can extend this simply to include observational uncertainty by just saying, okay, I'm going to assume that the observational uncertainty is also Gaussian and is independent of X and Y. And so then you end up just adding the observational variance onto the variance you had from the model for your emerging constraint X. And off you go to the races. So it's useful, I think, to point out that this methodology is different, but it turns out that it gives you an identical answer to just if you were doing a linear regression for the single constraint approach. So more complicated way of doing the same thing, but it has the huge benefit that it generalizes quite naturally to multiple emergent constraints. And the way that that happens is that you just add the additional emergent constraints to your vector of values and to your covariance matrix, and you start to see covariances between the different emergent constraints pop up, and off you go. You can extend this as much as you want. And in the paper, we show that this is equivalent to the other method that you might naturally pursue to combine emergent constraints of just doing multiple linear regression. So, and so you might have noticed that this method hinges on the ability to compute the inverse of your covariance matrix, which is needed by the multivariate PDF. And so you can't invert a matrix that isn't linearly independent in its columns. And so equivalently, this method becomes numerically unstable if you have constraints that are redundant with each other. And so a natural thing you can do to solve this problem is just throw out constraints that are highly correlated with other constraints. You can also use something more sophisticated and downweight constraints that show up multiple times. So, a symptom of being unstable is that if you change details, so the number of models you included, you get a very different answer. And on the right-hand side, I'm showing what happens if you repeat your analysis with one model thrown out. And so for the credible constraints, so these are the 4 that I showed in green on the previous, a couple of slides ago, it doesn't really make a difference. You get the same answer regardless. For all 11 constraints, it makes more of a difference. And I think this is because we're including the Voladin and Seiler constraints, which are quite similar to each other. So, okay, and so that's basically the method. Hopefully you all understand it. And so now kind of the punchline, let's look at the results. And so when we combine the 4 credible constraints, we should be looking at the red curve. So that's this method I just explained, and compare that to the CMIP 3 + 5 data. And so you see 2 things. First, you see that the PDF is shifted to higher ECS values. And second, you see that its uncertainty has shrunk, right? So it has a higher peak and shorter tails. And I could have told you that before I actually started with any of this math, because we've known for a long time that emergent constraints on ECS tend to predict higher ECS values. And they seem to be fairly consistent in that. And so the natural result is that we get a compression and a shift to the right. And that happens both for all constraints and for just the credible constraints. And then finally, I wanted to point out that we saw earlier that when we face these constraints with new data, that oftentimes they fail, or that the details of which models we include make a big difference. And this suggests that we're overconfident in our predictions of the correlation between ECS and the emergent constraint. And so the green line is what happens if you scale the fraction of the variance explained by a constraint by some amount. So in this case, we say that it's overfit by a factor of 3, and you see that you can shift the PDF back towards the CMIP prior by doing so.
2 minutes, Peter.
What's that?
2 minutes.
2 minutes? Okay. And so I'm just about done. Just wanted to point out that I think that subject to the caveat of assuming a multivariate Gaussian distribution, that this Bretherton and Caldwell paper solves the problem of how you might combine constraints. And the question that I'm left with is that kind of in retrospect, I'm not sure that there's anything surprising about this paper. It seems more kind of methodological, but I'm not sure that I understand more about constraints having been part of it. So what does it teach us? And so this last slide is just my recap, which where I've just rewritten the things that I wrote as punchlines from the previous slides. So I won't go through them again, but I'd be happy to take questions.